Today we start with next unit, dual nature of radiation and matter. We will study this unit in two parts. First we will take up photoelectric effect, and second part we will take up dual nature of radiation and matter. Now first we take up first part, photoelectric effect. Now in order to understand photoelectric effect, we have to understand certain terms. First term we have to understand is photon. What is a photon? A discrete packet of light energy is called as a photon. A discrete packet of light energy is called as a photon. Energy of a photon is given by the expression E is equal to h nu, or E is equal to h c by lambda, because nu is equal to c by lambda. Here E equal to h nu, E equal to h c by lambda, where h is Planck's constant with value given by h equal to 6.62 into 10 raised to power minus 34 joule seconds. Now in order to understand these two formulas, E is equal to h nu or E equal to h c by lambda, we have to solve some numerical problems. Assignment 11, because this is chapter 11 of our textbook, so therefore we mark it as assignment 11. So question number 1 of assignment 11, calculate the frequency associated with a photon of energy 3.3 into 10 raised to power minus 20 joules. And the answer would be 4.98 into 10 raised to power 13 hertz. Second question is, an X-ray tube produces a continuous spectrum of radiation with its shortest wavelength at 0.66 angstrom. Calculate the maximum energy of X-ray photon, and the maximum energy would be 3.009 into 10 raised to power minus 15 joules. So you solve these problems and verify the result. Now second term we are to understand is free electrons in metals. Now what are free electrons? We have to develop its concept. Now electrons are the fundamental constituents of atoms, hence of matter. All electrons are identical with charge E equal to 1.6 into 10 raised to power minus 19 coulomb, mass m equal to 9.1 into 10 raised to power minus 31 kg, and charge to mass ratio E by m equal to 1.76 into 10 raised to power 11 coulombs per kg. Now because number of electrons in an atom is equal to atomic number Z, and Z is very large for metals, therefore every metal has large number of electrons. Also valence band and conduction band coincide in metals, therefore here valence band and conduction band coincide in metals, therefore electrons in valence band are the part of conduction band, hence are loosely bound and are responsible for the conductivity of the metal. These loosely bound electrons can be easily taken out from the influence of nucleus to the neighboring points. Such loosely bound electrons are called as free electrons in metals. Such loosely bound electrons are called as free electrons in metals. Okay. Now next term we have to understand is work function. Okay. Work function. What is work function? The minimum energy required for an electron to escape out from metallic surface is defined as the work function of the metal. What is minimum energy? Minimum energy required for an electron to come out of the metallic surface, which is known as the minimum energy required for an electron to escape out from metallic surface is defined as the work function of the metal. Mathematical symbol, it is denoted by W0 or phi 0. W0 for thermionic emission or phi 0 for photoelectric effect, photoemission. Phi 0 for photoemission. Physical processes for electronic emission. Now there are 4 physical processes for electronic emission. First is thermionic emission, second is secondary emission, third is high field emission, fourth is photoemission. Thermionic emission, secondary emission, high field emission and photoemission. Now let us take up one by one. First we take up thermionic emission. Now thermal or heat energy is used to take out electrons from metal surface, then it is called as thermionic emission. Now if thermal or heat energy is used to take out electrons from metallic surface, then it is called as thermionic emission. For example, in vacuum tubes, tungsten filament FF heats up cathode indirectly, this cathode C indirectly, and electrons are emitted out. These emitted electrons are due to thermal emission. Now second is secondary emission. Now kinetic energy of primary electrons is used to collide with dynamic anodes. Okay, this is with primary electrons. P is primary electrons, Se is secondary electrons, these are dinodes. Okay, and so when kinetic energy of primary electrons is used to collide with dynamic anodes called as dinodes, and secondary electrons are emitted. Now current I is equal to I0 y power n, where I0 is the initial current and yn is the constant of secondary emission, where n is the number of dinodes. Okay. Now here you can see initially there is one electron, primary electron, it generates another secondary electron, and then these two primary and secondary electrons again produce 4 electrons here. Then here it becomes 8 electrons. Now 8 electrons produce more 8 electrons and so on. So electrons are getting multiplied with collision, on account of collision. So this is we call as secondary emission. Now high field emission. What is high field emission? Let us see. High field emission. On application of very high electric field across semiconducting materials, lattice electrons leave their places and constitute very high current to flow through it. This emission of electrons from lattice is called as high field emission. For example, Zener diode, field effect transistor are such devices which involves high field emission. So that we will learn about Zener diode high field emission in when we will study about Zener diode, its characteristics and then its uses. We will talk of high field emission. Now fourth is photo emission. Photo emission. Now what is photo emission? The process by virtue of which light of high frequency such as ultraviolet radiation is made incident on a clean metal surface and electrons are emitted out of the metal surface. This process is known as photo emission. The work function in photo emission is given by the expression F50 given by the expression phi 0 equal to h nu 0, where phi 0 is the work function of the metal, h is Planck's constant, and nu 0 is threshold frequency threshold frequency of incident radiation. We call it as threshold frequency, and it is known as threshold frequency. Okay. The work function in photo emission is given by the expression phi 0 equal to h nu 0, where phi 0 is the work function of the metal, h is Planck's constant, and nu 0 is the frequency of incident radiation known as threshold frequency. Now what is threshold frequency? Let us have the concept of threshold frequency. The frequency of incident radiation below which photo emission is not possible. The frequency of incident radiation below which photo emission is not possible, and above this frequency photo emission is possible. When the frequency of incident radiation is below nu 0, then no photo emission takes place. When frequency of incident radiation is above nu 0, then photo emission takes place. Here you see photo emission has taken place. The frequency here h nu 0 is the work function, and when it is h nu, where nu is more than nu 0, then photo emission takes place. Now above it is denoted by nu 0, photoelectric effect. Next slide. So threshold frequency is denoted by nu 0. Symbol for threshold frequency is nu 0. Above nu 0, photo emission will take place. Below nu 0, photo emission will not take place. Now we are to take up the concept of photoelectric effect. Next slide we are to see. Here look at the diagram. You can see the discharge tube with anode and cathode, anode A, cathode C, and anode and cathode are connected through a battery B. Positive is connected to anode, negative is connected to cathode. And MA is milliampere meter, which records the current flowing through the circuit, and V is potential difference measuring voltmeter. So V is voltmeter, which measure potential difference applied across cathode and anode. Now let us see how it is. Photoelectric effect. In 1887, Hertz made an observation. What was Hertz's observation? Let us see. When a photon of ultraviolet radiation was made incident on the cathode of a discharge tube, it made the passage of current easier. So look at the circuit. UV radiation is made incident on cathode. This is UV radiation, this is cathode, made incident on cathode, and electrons, 4 electrons are emitted out, and this made, because number of electrons has increased in the tube, now this made the current flow through the circuit easier. These electrons are accelerated under potential difference V from cathode to anode, and potential energy EV of the electrons at cathode is converted into kinetic energy of electrons when they reach anode. So this was Hertz's observation. So when a photon of ultraviolet radiation was made incident on the cathode of a discharge tube, it made the passage of current easier. Next, Hall-Watch made another observation. 1888, 1 year later, Hallwatch made an observation that when a zinc plate connected to GLE means gold leaf electroscope, was given negative charge, the leaves of gold leaf electroscope diverged. So here undiverged leaves, here diverged leaves when zinc plate is given negative charge. Now when zinc plate was exposed to UV radiations, okay, in the third diagram, zinc plate is exposed to UV radiation. So when zinc plate was exposed to UV radiation, leaves of GLE collapsed. This revealed that negatively charged electrons have been emitted out of zinc plate. These are negatively charged electrons which have emitted out of zinc plate, and zinc plate has become charge free. So the gold leaf electroscope collapsed. Now photoelectric effect defined. On the basis of these observations, photoelectric effect was defined. The effect, photoelectric effect, is the effect by virtue of which electrons are emitted out of photosensitive metallic surface when exposed to light of high frequency, such as ultraviolet radiation. Okay. Photoelectric effect is the effect by virtue of which electrons are emitted out of photosensitive metallic surface when exposed to light of high frequency, such as ultraviolet radiation. So this type of emission, if take place, then we say photoelectric effect is taking place. Now Leonard's laws of photoemission. When photoelectric effect was defined, Leonard gave two laws of photoelectric emission. First, he said that the maximum velocity of ejected electron is independent of the intensity of incident radiation but depends upon frequency of incident radiation. First law, the maximum velocity of ejected electron is independent of intensity of incident radiation and depends upon frequency of incident radiation. And here is the graph, stopping potential versus frequency graph, straight line. Second law, the rate of emission of photoelectrons is directly proportional to intensity of incident radiation but is independent of frequency of incident radiation. So here the graph between photoelectric current and intensity of incident radiation for a particular frequency. Now Leonard did not give any proof for his laws. Then Einstein tried to give theoretical proof for Leonard laws through his famous equation, Einstein's photoelectric equation. In 1905, Einstein treated photoelectric effect and gave a theoretical proof for Leonard's laws. He used Planck's idea. What was Planck's idea? Planck proposed that a photon of light has energy equal to h nu. A photon of light has energy equal to h nu. Einstein used this idea and derived his famous photoelectric equation. He said that when a photon of light energy h nu is made incident on a photosensitive metallic surface, its energy is used up in two ways. First, a part is used up in overcoming electrostatic forces of attraction between electron and positively charged nucleus, that is as work function, and the other part is used up in imparting velocity to the ejected electron. Then according to law of conservation of energy, h nu is equal to h nu 0 plus half mv square and is known as Einstein's photoelectric equation. where h nu 0 is the work function of the metal and half mv square is kinetic energy of emitted electrons. So this was photoelectric equation, h nu equal to h nu 0 plus half mv square. Now alternative forms of photoelectric equation. First, we can write photoelectric equation as half mv square is equal to h nu minus h nu 0. We take out h common, here h common, and we write within bracket nu minus nu 0. Now when an electron is accelerated through a potential difference of v volts, then kinetic energy is equal to EV, electron into volt, potential difference, charge on an electron into potential difference. So we call it as EV. Kinetic energy is equal to EV. Einstein equation can also be expressed as EV is equal to h into nu minus nu 0, because half mv square we can replace it by EV since they are equal, where V is called as stopping potential, or V is equal to, also we can write it as V equal to h by E into nu minus nu 0, where V is stopping potential. Now what is stopping potential? Let us take up what is stopping potential. We define stopping potential, that negative anode potential for which photoelectric current becomes 0. That negative anode potential for which photoelectric current becomes 0 is known as stopping potential. So it's another important term, stopping potential. Now discussion on photoelectric equation. Now Einstein photoelectric equation is half mv square equal to h into nu minus nu 0. Now first case, when kinetic energy is 0 or v is 0, velocity is 0, thus velocity of ejected electron is 0. The electron is just free from the metal surface. They do not come out but become free from metal surface. 2. When nu is less than nu 0, then kinetic energy becomes negative, which is not possible. Therefore photo emission is not possible below threshold frequency. Third case, when nu is more than nu 0, kinetic energy is positive. Photo emission takes place. If nu increases, velocity of ejected electron also increases, which shows that velocity of ejected electron depends upon frequency of incident radiation and is one of the Leonard's laws of photoelectric emission, as stated above. Thus Einstein gave a theoretical proof of Leonard's laws. Okay, now we go to assignment of this topic. The information that we have learned, we have to solve some numerical problems. Assignment 11, question number 3. The following table gives the values of work function for few photosensitive metals if each of these metals is exposed to radiation of wavelength 300 nanometer. Which of these metals would not yield photoelectrons? Now we see here we see that metals are sodium, potassium, molybdenum, and work function is 1.92 eV for sodium, 2.15 for potassium, 4.17 for molybdenum. So when we calculate energy associated with wavelength 300 nanometer using E is equal to hc by lambda, that comes out to 4.13 electron volts. So molybdenum will not yield photo electrons because its work function is 4.17 electron volt, more than 4.13 electron volt. Now question number 4. By how much would the stopping potential for a given photosensitive surface would go up the frequency of incident radiation were to be increased from 4 into 10 raised to power hertz, 10 raised to power 15 hertz to 8 into 10 raised to power 15 hertz. Given h equal to 6.64 into 10 raised to power minus 34 joule second, E equal to 1.6 into 10 raised to power minus 19 coulombs, C equal to 3 into 10 raised to power 8 meter per second. His powers are not given, so you are to use the power as I have spoken. Now question number 5. Light of wavelength 3500 angstrom is incident on two metal surfaces. So here you have angstrom is incident on two metal surfaces A and B. Which metal will yield photoelectrons if their work function are 4.2 eV and 1.9 eV. So when we calculate energy E equal to hc by lambda for wavelength 3500 angstrom, it comes out to be 3.454 electron volt. So metal B with work function 1.9 eV will yield photoelectrons because energy of incident radiation is more than 1.9 eV and less than 4.2 eV. A will not yield photoelectrons, but B will yield photoelectrons. Now question number 6. Calculate kinetic energy of photoelectrons in electron volts emitted on showing light of wavelength 6.2 into 10 raised to power minus 6 meter on a metal surface having work function of 0.1 electron volt, and kinetic energy would come out to be 0.085 electron volts. Similarly, we look at question number 7. The photoelectrons are to be emitted from a potassium surface with a speed of 6 into 10 raised to power 5 meter per second. What frequency of radiation must be used if threshold frequency of potassium surface be 4.22 into 10 raised to power 4 hertz? So frequency would be 24.4 into 10 raised to power 13 hertz. Now these are 7 questions which are to be solved by you. Okay. Now thank you so much for listening patiently. I hope you would like it. God bless you. Thank you once again.